I went to U of I, as was said at the beginning, but I never got a chance to come out to Michigan. Got to Wisconsin a few times, Chicago many times, but never this far east. It's just like I remember. It's December in Michigan. It's like December in Illinois. Lovely shades of gray, and allows you to focus on your work. So it is a treat to be here, and I'm looking forward to the opportunity to talk to you a little bit about what NOAA does. I saw the last couple of years of Spencer lectures, space physics, and I know somebody you're very well familiar with, Thomas Buchan, who now is over as the NASA Science Mission Directorate head. He and I chatted a couple of times since he came over in the past month and a half, and he talked glowingly about his time here. And I warned him about what he was getting into at Science Mission Directorate, because I was there for about 12 years. So it's a real treat for me to be able to talk to you about what we do at NOAA. Having worked at NASA for 25 of my 30 years in the field, and then now NOAA for 2 years, I've had an opportunity. I've been privileged to have an opportunity both work on NASA and the NOAA side, all in Earth observation. Well, all in space. Half of my NASA career was in space physics and space science, and the other half was in Earth observations. But all of it is working from space. So I'm going to talk to you a little bit today, about, the title is the Integrated Global Environmental Observing System. And it may come as a little bit of a surprise that, we're NOAA, we're weather, so why are we worried about the global system? But it really is, as you'll hear, many of you already know, the weather is global, the models are global, and our observing systems are global as well. But I think the part I want to leave with you is focus on the integrated side. And the fact that it's not just a series of individual measurements, but it's how we're bringing these all together that is really where we're getting on the threshold of a real breakthrough, I think, in what we understand of the planet and of the atmosphere and the environment. And it's enabled by our observing systems and our integration of those of the same. So the sort of an outline, I think it's this way. We'll talk a little bit about NOAA and the NESDIS missions. I'll bore you a little bit with org charts just so you get a feel for what our piece is within the bigger picture. Also relevant to NASA, because I know many of you have more experience working with the NASA side of the house. And then just jump right over to challenges and opportunities. So as I've come to know in the last 2 years, as you'll see, we're on the threshold of a delivery of a number of new observing systems. And as soon as in our business, an observing system has a generation of about 20 years or 25 years from when you, it's about 20 years from when you think of it to when you field it, and another 20 years from when you field the first one to when you better start fielding the next one. So we're talking about a generational change now with the system that we're deploying right now, which means it's time to start thinking about what are we going to do next as we think about evolving the system, bringing in new capabilities. So we'll talk about the opportunities and challenges that come from that. And some of these are the kind of challenges you'd like to have. For example, too much data, how do I deal with it? Too many sources, and how do I integrate them? And too many questions to answer, how do I prioritize? What do I focus on, and what do I leave to somebody else? So those are the challenges we're dealing with. And I tried to put in here, you'll see, where different players can fit into it. It's not all big organizations, big companies. It's also individuals, and how the role of an individual can be in having an impact on the global system. So NOAA's mission is broad. It involves climate adaptation and weather, and providing a weather-ready nation. We're responsible for monitoring the health and viability of the feedstock, the fish stock in the oceans, at least as far as the U.S. is concerned. We have a responsibility to give information and services to the community so that they're resilient and ready for extreme events and for just a climate change where you have rising waters, et cetera, and how the communities deal with it. So we're an environmental information agency. So we provide that to the communities around the nation, and in a larger sense, we're part of a global community. So what we learn, we're actually a model for many agencies around the world to do the same thing. So we work in many international organizations as well. The Weather Service is going through its own evolution from ground-based radar sitting in local areas to integrated radars and integration with the satellite data in a way that they hadn't done in the past. And we get to go ZAR, you'll get a feel for that. And also we do this by investing in our observational infrastructure. And about half of our budget, about $2.3 billion a year in NOAA's roughly $5 billion budget, goes to our observational systems. And that's not just satellites, that's ships, airplanes, radiosonde balloons, ground radars, and all the infrastructure, the data systems, the analysis to support all of those. So that requires not just investment to deploy a satellite or a ship, but to maintain it, to upgrade it, to add the researchers to it, to put the instrumentation on it. So it is a significant investment annually to maintain that observing system, which has customers. Every one of you and everyone in the nation is a customer. And to do this, we have to keep evolving our organizational, our capabilities, our people, because these systems have to stay current and state of the art, or they're going to be irrelevant and go away. I put this up. I don't want you to read everyone, but the point I put this up in is, and these are our different pieces of NOAA, the Weather Service, the Fisheries, Marine Fisheries, Ocean Service, and Atmospheric and Research. This is not just a random selection, but these are the major program areas within NOAA. So I challenge every one of you can find yourself in several places in here, either how you're impacted by it or how it may be an area where you're doing research. So where we are touching in our operational activities on a regular basis in our research activities really do cut across more than just providing weather forecasts and warnings, which is what we're known for. In the weather part alone, we've added, we have not just weather, but also aviation weather and volcanic ash. So we have satellites which monitor the atmospheric chemistry, and then whenever there's a volcano, we have a volcanic forecast center, which uses the observations and looks and atmospheric propagation to say, well, so where are those clouds going to go? What's in the clouds? We can measure those. And the aviation industry is keenly aware and sensitive to that. They reroute thousands of planes a year based on our volcanic forecast warnings. And we're part of a global community that does that. We have a swath of the world from the Western Pacific to the Western Atlantic, and the Europeans have it from the Western Atlantic to the Urals, and the Russians from the Urals over in the Japanese. So it's, again, a coordinated activity that happens around the world. One thing that struck me when I came to NOAA was the size of the international relationships is enormous in terms of the partnerships that we have to do all these. So this is just an example of the technical areas, and they're supported by NESDIS, and also down here would be OMAO, our ships and airplanes organization. So we have to support all of these, and we have to figure out how to do that in a prioritized way. And this shows where you stand within the organization. There are different line offices, and I won't go through these in detail, but just show that each of these has their focused objective, and they all feed up as part of the NOAA organization. So you may hear the term NOAA Fisheries. That is a NOAA responsibility as part of the Department of Commerce to set fish stock requirements for a number of really high-value economic fishing around the globe. And that's probably where you see there are more lawyers in fisheries than there are anywhere else in NOAA. And they get a lot of interest because the cod fishermen or the shrimp farm fishermen or all those or the trout or all the rest are interested in them all the time. We're not the only space agency. As you well know, we have NASA along with NOAA, and the USGS and the Department of Defense are all their agencies within the US alone that do the space part. And this is an interesting chart, shows you sort of where the centers of gravity are. Often hear that there is a NOAA-NASA conflict. Why does NOAA do it? NASA's doing earth science. Why is NASA doing earth science? It's NOAA's job to do weather. And it really is, neither of us can succeed without the other, and both of us have a critical role. This is where you see a lot of the research, the development for earth science research, but also satellite research, in technology research. And we take that and focus on observations and applications. We don't focus on the research as much as is the research, how do I apply the research to the user, to the community, to the services? And that's not something NASA's going to do. And it is a significant investment. And we take what are one-of-a-kind demonstrations, we turn them into selected ones that we think are important into continuous operational deliverables. And that really, as you'll see, is a key element of what NOAA does, is the reliability side. We're a 24/7, 365 operation. And that really means that if a satellite goes down or if a hurricane takes out Washington, D.C., where our primary ground systems are, I have to switch over to a backup within 15 minutes of all of my operating satellites, all of my data product generation. So I have a backup system 300 miles away, which has automatic switchover and power supply set up, and in a different power grid, which we set it up for that reason, et cetera. So that's the kind of reliability redundancy that's built into our system to provide that essential services. And you'll also see that builds in a level of conservatism to change that is not what you're going to see in a research organization like you're in. You may have a great idea, but it's okay, but I got to make sure I don't break anything. So there's always that kind of tension that you'll see between these two organizations. So the NESDIS part of NOAA. You saw NESDIS is that we're the Satellite and Data and Information Service. So we provide all of the remote sensing satellite operations. We provide all of the data down and communications. We provide the archives, the National Archives of Environmental Data at our Asheville, North Carolina Center. All of those things are, and those data are then available on free and open to the world and to the US particularly. But so our vision, we have to provide that global environmental data information to satellites and other sources, so it's ships and airplanes as well, to provide for the protecting the nation's requirements. And also our vision is to expand that understanding of the planet and to be the trusted source of data. So the trust part is where it gets into validation and calibration, that we have to validate the quality of the data. So how do we do that? For within NESDIS then, in research, your ideas start with a question. Why? I want to do this. I want to learn. I want to understand better a phenomena. With us, it's the same, except it's the users. It's not, it would be really cool if I knew how hurricanes, why they rotate left instead of right, but if that doesn't matter in terms of the impact, it's not a question I'm going to address. What do the users need? What do they want? Do they want to have shorter warning times or longer warning times for tornadoes? Do they want to know what the high tides are going to change over the next 20 years? And then that comes back. So we understand user needs, and then we figure out how do we address that need? How do we get the data to inform that? We can build it, which is to build our satellites, what we've done for 50 years. We can borrow it. We have partnerships. We use NASA data. We use European data. We might use Chinese or Russian data or whatever. Right, Chinese or Russian have different problems, but I'll get to that in a little bit. Or we can buy it. A lot of times we buy data. We pay airplanes to fly transponder, data set collectors on the airframes to get data on the flight routes, and we use that in our modeling. We buy radar data in local areas and things like that. But we look at the trades, and we constantly are revisiting these trades to see what the best way is to meet that particular need. And not every need requires a satellite. We might send it to somebody else. If it's a balloon, can do it as well. And then once we get that, we mix it all together. And then we provide the data in near real time. That's the 24/7 part that the Weather Service needs. And we're talking about terabytes of data per day in near real time with sometimes, like with GOES, with 5-minute latency. So a 60 megabyte per second data rate with a 5-minute latency for the Western Hemisphere. And that's broadcast to the whole Western Hemisphere. We archive it so that it's available for the next 100 years. And that means long-term archiving requirements. And we use data and conduct research. How do we make a best use of that data? And this is sort of the data science and data analytics, how to manage the data and how to make it more useful and addressable. And from a NESDIS perspective then, that's a life cycle which then comes right back on itself. Starting with the user needs, figuring out how to make it useful, and that goes back into informing the users that I have a better way to do something that you didn't even know we could address. So knowing how to use the data and how to collect it and how to present it and how to prepare it gives us information, and our context with the users up front and throughout the process allows us to go back and give the users some feedback. We can tell you, for example, we can tell you what the ocean color quality is, your coral bloom in the Lake Erie. We can do that from satellites now, and we can do that with a regular data product using our VIIRS instrument. So we can tell the lake that Toledo should shut off their intake. There's an example where they had a major bloom, algal bloom in Lake Erie. We were projected it far enough in advance they could shut off their intake valves, so they didn't flood all that stuff into the water treatment centers, which would take weeks to clear out. They shut it off while the bloom went away. And that kind of advanced notice is something that they wouldn't have thought of on their own, but in the development of research we came up with that we could able to produce that from space. So how does NESDIS meet these different objectives? Uninterrupted satellite operations, that's the easiest and the most obvious, not the easiest. We build and define the next generation of satellite systems. We also provide the data processing and operational product distribution, and this is a big deal. For GOES and JPSS, for example, we're talking about a $3 billion investment in ground distribution services to download the data, crunch the data, turn out products, and deliver it in near real time. We develop the products, as I mentioned. These are just some examples of I'll have a follow-up in a minute. And then we provide the long-term and stewardship and for all these assessments over time. And each of these has different kinds of products. So I'm going to show you then, as an example, what is the recent, so that's sort of the compendium of what NESDIS does and what our guidelines, our mission requirements are. So I talked about being on the cusp of a generational change. Typically, NOAA would launch a satellite every 3 to 4 years. But we're in an age right now from January of 2015 to about this time next year, we will launch as many as 5 satellites in about 2.5 years. That's much faster than before, but it's this generational change. This is a series of the satellites we're looking to launch, which are summer continuity. This is an altimeter measurement. First time we do a space weather measurement with Discover from L1. First time we have an operational radio occultation constellation from LEO, and 2 new series of satellites, GOES and JPSS, which I'll have a little more detail. GOES-R is the biggest one, the most one that was launched 2 weeks ago out of Kennedy Space Center, Cape Canaveral. It is the first new technology from GEO for the U.S. since about the early 80s when we designed the current geostationary operations that we have right now. And just as a backup, what we fly right now, the GEO requirement is real-time imagery of major storms of the continental U.S. with a 15-minute latency. So we have a satellite over the western central Pacific and a satellite over the western Atlantic, and they have complete coverage of the entire western hemisphere from about 80 to about 75 degrees plus and minus south. And there's overlap in the middle. And we have a third one sitting in the middle as a spare. So if either one of those 2 satellites goes out, we turn on the spare and we're back up again within a days. Well, we're instantly with the observing, but in days we get back into position. So that's that redundancy that we have up there. We've been flying those since 1970s, early 70s. GOES-R was conceived in the early 90s as the idea, and we started building about 15 years ago. This is the first new build, and the major new builds are across the board. A new imager, and we'll talk about that in a moment. The first time we're flying ultraviolet imagery from geostationary. GOES is not just Earth observations, which are these 2, but also space physics and solar. First time with improvements in all of these measurement techniques. And the first time we're flying what's a geostationary lightning mapper, which actually can look down and measure every flash of lightning in the Western Hemisphere and record that back in near real time as well. And I have a chart on that later on. So what GOES-R does is now GOES 16th in its orbit. It has 3 times the number of channels, which means greater information density. And we have multiple infrared channels now, which can tease out different altitudes of clouds, different types of clouds in a way we've never seen before. Has 4 times better resolution. So instead of 10 kilometers or 8 kilometers, depending on the band, you're down to 2 or even half a kilometer resolution from GEO. And it has 5 times the scan speed. So this is like a high-speed camera snapping pictures. So instead of taking 26 minutes to do a full disk image, you can do it in 5. So what that means is you can stare and see real-time significant storms happen. And with the 5-minute latency folded in, it allows you to actually not just watch what happened half an hour ago, but watch what's happening now and watch it with greater precision and greater resolution. Here's an example of what we have on orbit now. This is GOES 15. We have an engineering mode in our existing systems which allows us instead to run it at 1-minute updates. And we don't do that often because it wears it out, but we do this for testing. This is what you're used to seeing if you look at your evening news and you see that picture of a hurricane or whatever. This is the kind of refresh rate you would see. This is at a 1-minute update of that same image. Now double this and also add the resolution, 4 times the resolution to this, and then add different bands. So then you can imagine if you're a researcher what you can do with this kind of information. But if you're an operational weather forecaster and you want to zoom in on just this zone, you can see, as you get in, you can see severe storms occurring in cities and in towns and in counties in a way that you can't see or you wouldn't be able to use in the current system. So this is what was launched just last week and will be operational in a couple of weeks. So just to show that we're not all, we're not all bored. This is the image from the GOES-R launch. That's the Atlas V. A nighttime launch at 7 p.m. out of Florida. Cygnus won't look quite this nice because it's a different kind of launch. So just to give you an idea of that, it never gets old. The 2 loudest voices on there, one was the Secretary of Commerce, her first launch, and the other was the director of NOAA, Dr. Catherine Sullivan, who actually flew in space 3 times on the space shuttle. but she was the loudest one there cheering it on. So it never gets old watching launches. That was both of their first Atlas launch anyways. My first Atlas launch as well, and I've seen about 15 launches over the years. So the other piece is the low Earth orbit, and that's what the JPSS is. So the JPSS, Joint Polar Satellite Program, it's basically a bus, and it almost is bus size. It's a stretch minivan, if you will, of a whole suite of different instruments. Sounders for weather, imagers, the VIIRS imager here. If you're familiar with MODIS, having seen that data from NASA over the years, VIIRS is MODIS with a couple of different channels, but roughly the same resolution and swath. There's a radiation budget measurement for measuring the inflow and outflow radiation of the planet. And there's a ozone mapping, which not just measures ozone, but also other atmospheric constituents for atmospheric chemistry. This is an incredibly capable suite of instruments. We're flying right now on SUMI NPP, flew in 2011. This is the first one of this 4-bus series to launch, and will launch next spring. To give you an idea, so we launched this very capable set of instruments. This is the primary set of products that we come out of this. I'm not going to go through each of these, but you can see in each of these a major investment in information and content, and this is what we commit to delivering. So you look at each of these, and every satellite produces dozens of products, and we have to support these on missions. And each product is tailored. Each product has a lifetime of research, or many lifetimes when you add in. I mean, if I were to look at any one of these, I could probably pick a quarter of this room, and that would be the career of this group of people to develop the cloud optical thickness product in a way that is reliable and dependable and will work for the next 20 years. And that's the kind of investment it takes to provide this. For example, and there's different latencies, qualities, processing requirements for each of these, which are tailored and developed as well. Like the GLM on GOES-R has a 20-second latency I mentioned. Where the Ocean Color products out of VIIRS, we might have hourly, weekly, monthly products that come out of it, depending on the user requirements. I want to give you an example of just one of these, the Total Precipitable Water product that comes out of JPSS, to give you an idea of what it means, what it takes to put something like this product together. The reason being that it's not just instrumentalists that are necessary. It's instrumentalists and software engineers and use engineers and designers who work on it as well. So this is a daily image of the total precipitable water. And this basically tells you how much water is in the atmosphere that could come out as precipitation. So am I going to get rain? And you look, and here's the scale in millimeters. So from 0 to 70. So it's very dry in the cold areas. Over the desert, very dry. Lots of water sitting around the tropics. And so we'll talk a minute about what you do with this, but how do you generate something like this? You don't get there's not a water channel that you dial to on a sounder. And this mostly comes from a bunch of different places. So you have to figure out from the microwave radiation, from microwave monitor observations, how to get this product. So how do we do that? We start with the operational raw data we get. So we have ATMS, which is one of our primary sounders on SUMI NPP. The Europeans have something on their MEDOP, which is their version, flying at a different time zone. They use as well. POSE is a legacy mission, has an AMSU sounder, similar, different generation sounder, different product shape and type, but the same measurement. And the Defense Meteorological Satellite Program has their own microwave imager, which they use. So each of these produces data, which are then, this is I would call a community product. It's not merged yet, it's community, because they all provide the same sort of thing. But what we have to provide is that when we bring these together, we don't have this thing which is all different colors. The calibrations have to be the same. They have to be consistent so that you can bring these together. We bring with these also other environmental data, experimental satellite data, like Aqua has an instrument, GCOM has a AMSR instrument on it. GCOM-W has a different microwave radiometer. We bring in research satellites and feed those in. TRIM actually measured directly the rainfall in a cloud. So we bring those in as well to inform and to calibrate those. And we also have ground truth that has to be folded in every day, 4 times a day or 5 times a day at various places. And these are locations where the radiosondes, the balloons, are sent up. So every day there's an infrastructure of radiosonde deliverables, which feed into the ground truth calibration of these satellite observations, which allow us then to take this and fold it into a daily total precipitable water data product. That's one product in that set of about 70 we saw on the previous page. And this is sort of the microwave integrated retrieval system that we have, which is this community product developed by, and NOAA's that pulls all this together. Other, MEDOP probably does the same, UMETSAT does the same, but they use this product as well. And that gives you an idea, the amount of work it takes and the effort and the integration over time in a generation to develop these kind of products that are useful for regular basis. And that's really, that's the start of it. And the next step is, can we blend these together so it's not just static? And this is an example of taking these and then blending this with the models to actually use this as a propagation tool. So you have the input data, which you've now made sure the calibrations are accurate and consistent. And the data are up to date. And then you put these into a forecast blended model, which does interpolation, which doesn't have those gaps, et cetera, and then propagates that future so others can look at, so forecasters and other modelers can say, so what do I do with this? And how do I zone in and see whether I've got a monsoon coming in the south, in the Bay of Bengal or something like that? So that's just the next step from a sort of a community product to a true blended product. And every one of those might have similar nature products like this. And that is just the start, if you think about it, because suppose we want to know not just whether it's raining, but where the water is going and is it going to go at the right way, at the right pace? Are we going to have floods or drought? So we take, with the combination of that measurement here, which was the water in transition, sort of the water in suspension, we have other observations, which takes the static case of water. There's water underground, there's water in the rivers, soil moisture measurements. Taking those two together tells you have the static water, water in transition, and then we have to fold in the models, which is where is it going and how's it going to get there? So we have hydrographic and hydrological models which say, what does the terrain look like? What is the downstream? Have they had water, a lot of water last week, so their saturation levels are low? So our services come out to then, what is the floodplain going to look like downstream based on the water we're measuring now and on the soil moisture and other preconditions we've already identified? So this is the research side, which is really, and this is not NOAA only, this is NOAA and the USGS and the Department of Interior and the Corps of Engineers and state and local managers try and use this. Figuring out how to present and prepare this information is really a key challenge. I'll give an example. For a long time when we talked about storm surges, we'd say it would be X feet above flood level. So if you live on the coast, it's going to be 3 feet above flood level. And does that mean anything to somebody who knows where their flood level is? You know where your flood level is? You know, is it here, is it here? You may not know. And people were not reacting to it. And we did some research, the Weather Service did, and said, so they changed it to say it's going to be knee high in this region. It's going to be waist high. So and it was the same information, but communicated in a completely different way. And that got people to respond. So in other words, 50% of your streets are going to be flooded with 1 foot of water. Forget about flood level stage, which was useful for flood managers, but useless to everybody else. That kind of social feedback is something which it's taken us time to learn and to understand. So how you present this information is just as important as about how you gather it. So that's just a sampling of one product on one satellite system, and we have dozens of such products. So as we try and evolve, so you can imagine the infrastructure we have. So as we try and evolve to what are we going to do next, what are the challenges that we face in developing the next generation and while maintaining the current one? Maintaining the current one is the primary one, is that people are used to a particular set of services. They need to get what they've been getting to date. And you can't just make it better. It's like the analogy, if you remember when we went to HD TV, how much of a panic that was for everybody who only got broadcast and they weren't ready for it. And that's just for getting the evening news on TV. Let alone if you were to turn off their phones and say, oh, you haven't got your upgraded phone yet, so what, you're out of luck. We can't do that. We've got to make sure the continuity is consistent. And that means understanding the dependencies on how are the users going to be affected by any changes, and how do we make sure that we have solutions which prevent that from ever becoming a critical event. We have to improve the quality going forward as customer requirements change. Climate change is a reality, so there's going to be greater interest in severe storm events, maybe in storm surges and in floods. So we have to be ready to provide that in a more effective way. Air quality may be a different issue, water quality. These are things which have not traditionally been a big deal, but may be coming back. So we have to collaborate and anticipate those new missions so that we can do them in a timely fashion. We have to leverage the research of our partners. NASA is one, but the Europeans, the Asians as well. And we have changes in the IT landscape, which I think are even more key. How do you get that information to the user? Most people don't watch the evening news anymore. So do I get it to your cell phone? Do I provide it as an internet? Do I get rid of broadband and just say everybody's going to get it on the internet? How do I get the information? So And how do I deal with hacking and with invasions and with instability of our platforms? These are parts of our continuity challenge to us. And the third is, how do we do this in a changing economic and social environment as well? So we have new partners, and you'll see a chart in just a minute and opportunities of where that comes in. We have many new players in the Earth observing world. It's not just NOAA and EUMETSAT and JMA. It's the Chinese. There are many different agencies around the world, and there's now commercial people trying to get involved. So how do we manage that? How do we prioritize what the government spends its money on and what we let other people's do? And how do we manage the service continuity risk with this complex system? If somebody's going to provide it for me at a lower cost, it may be a lower cost today. Is it going to be here in 10 years? And if not, do I have to pay to get it to reinstate it? And maybe we walk away from it. So how do we balance that risk as we go through these changes in the system? So I'll give you just a quick example, continuity risk. This is what we call a flyout chart. It shows by calendar year or fiscal year the launch schedule for different satellites. If you look at this, you might notice, if you're sensitive to this, this is an older satellite. If this were to fail on launch, which is launching next year, and that happens 1% of the time, we would be in big trouble. These old satellites are going to be gone. This one's going to be old, and we have no backup. So if this satellite fails on launch, we have a problem we have to deal with. So we spend a significant amount of time figuring out how we mitigate that kind of failure. And we look at this across all of our constellations. Another example is, how do we operate the systems we have, and how do we ensure the integrity is solid? Don't worry about the graphic here. It shows our satellites and our ground system and how we get data to the users. You might think of this outline of yellow as a firewall. We have to make sure that anything that gets into that wall is secure and safe and accurate. So it's the quality of the data, but it's also the security of it, because we get attacked or hacked thousands of times a day. I wouldn't say it's attacked, it's probed to try and get into our systems, because we have great systems, a lot of data. There's a lot of interest in that. So we have to make sure that our systems are secure as we go through this. At the same time, our mandate is to provide free and open data to the world, every time, all the time. How do you do that at the same time? And one of the ways that we're trying to do that is to provide for secure ingest and then have different cases of users. This is the black boxes. Nobody gets into this other than the people we know. And this is non-real time, which is open to the public. So we have to design systems. This is easily done on a PowerPoint slide. But when you talk to NSA or you talk to the intelligence agencies, how do you do this on a system which is pumping a gigabyte of data every day with a 5-minute or 15-minute latency, and validate every one of those bits so that it's still accurate? That's not easy to do this secure ingest. It implies significant computing power to do that. So you don't do that on everything. You only do that on pieces of it, so that otherwise you would just kill yourself with the overhead. So those are just a couple of the challenges, and they're all, as you say, are related to continuity. But the opportunities, I think, are even more significant that we have as we prepare for the future observing systems. And one of the greatest opportunities is that we have a much richer set of data observations right now. This is what we've had in the past. NOAA flies its satellites and spends a lot of time and effort deploying and exploiting our satellites. But this is a very narrow view of the world. This is what the world really looks like in terms of capable Earth-observing satellites that are out there. Dozens of them, and you can't read them all here, but Europeans in their Sentinel program are launching on the order of 20 satellites in the next 10 years, which are all very capable and highly reliable, and we have to figure out how to use them. The Japanese are a partner on several of our satellites that we use. And NASA has research satellites which are very capable and may last for 15 years. TRIM lasted from 97 to 2015, 18-year mission. We never really developed it as well as we could have because it was a one-off experimental mission that might go away right away. That's not going to be the way that we can work in the future. So what we do have is partnerships set up with many of these organizations. These are just the satellites that we have partnership agreements for data exchange on a real-time basis. We're working on additional partnerships with the Koreans who are flying geostationary, with the Indians who fly geostationary, emerging partners. These groups weren't around 20 years ago in terms of the quality of the data. And there are other partners which aren't circled here. You have the Chinese data and you have the Russian data, which have other issues when it comes from data security, that the data are interested and available, may not be available for secure ingest on a regular basis because of security concerns. But the challenge is to take advantage of all these, and that's really one of the thrusts that we have within NESDIS, is to figure out how to do that in a productive way. The other opportunity is really comes out of small sats and miniaturized instrument technologies. I mentioned the minibus that we have, and that's how we fly our satellites. That's one approach. Big, very capable systems that are highly reliable and also very expensive, on the order of $2 billion a satellite. That's the amortized cost. It includes research, development, operations, data products, et cetera. And that works for a while, but it is single fault intolerant. You lose a launch, you lose $2 billion. And also you have a hole you've got to fill. But there are new technologies with small sats. You guys, I don't need to tell you folks about that because that's part of your bread and butter. The challenge for us is how to take advantage of that in a way that meets our other needs. And this is just one example where NASA and MIT have been flying something called Murata, which is basically a microwave sounder instrument in a CubeSat technology. This is a 3U. I think this might actually be a CIS 3U. We've taken that and looking at building something called EON microwave, or Earth Observing Nanosat, which can replicate by itself one of our instruments, that ATMS, the Advanced Technology Microwave Sounder. This is about a $30 million instrument plus operations plus development, whereas the ATMS is $130 million for one instrument. We're buying 4 of them or 5 of them. So one instrument is about 4 times the cost of this whole platform. Of course, that one instrument will last 7 years, and this might last 2. But still, if I can build 4 of these, or I can build more of these, can I use these effectively in a way that I can use for my operations? So there are all kinds of challenges to that, is that if I have 4 of these, they might all have different calibrations. I got to manage 4 calibration systems. They might drift at different rates. They might age at different rates. So I have to continuously bring in new satellites and instruments into my system. And that's part of the challenge. But the opportunities are certainly there. And this is just one area where miniaturization might work. So from an operational point of view, we have the similar challenge of how to bring these measurements in. So you have Cygnus, which is flying in about a week and a half, a week from Monday. So Cygnus provides one piece of information which can be very useful to us, which is potentially ocean winds, but also storm intensification and cyclones and tropical storms, which is on that product list is something that comes out of our sounder information, which the Hurricane Center can use. But it provides it in a different time zone, a different methodology. It doesn't have swaths and long and regular. It has slivers, slices through the storms, and sort of asynchronous with everything else we do. So we need to figure out a way, and this is what we're working with Chris Ruff and with NASA, to figure out how can we learn from your demonstration and figure out how to merge this kind of measurement into our system in a way that's productive, and maybe buy 5 more of these or 10 more of these if it turns out to be a productive way to make the particular measurement. But it's not the measurement that's the challenge, it's the integration of the measurement into the system and into the operating system and into the decision support system. That's the real challenge that we have to face on the operational side. Tropics is another example. It's a 12 satellite constellation being built. It's another NASA Earth Venture mission, which is a similar challenge that we're trying to work with now in the same ways, is how to handle constellations. So if I were to challenge you folks here, think as you look at constellation satellites, how do they operate as a virtual observatory? It's not just a bunch of individual data sets or observations. It's an integrated observing system, and how can you make that look like it's just an observation, not that's Cygnus. Eventually you're going to say that's Cygnus 3, and I know Cygnus 3 looks a little different from Cygnus 4, and it always does that, but that's all cool, but we have to figure out how to make it into an integrated observing system. So participating in the calibration and validation, what NOAA wants to do, working with the different teams, the Cygnus team with you guys and with Chris Ruff, the Tropics team with MIT and with NASA, to figure out how we can make these research missions demonstrate an operational capability and maybe turn it into an operational asset. In the space weather side, we have a similar challenge, but in a different way. We're just getting into the space weather field. We're flying GOES-R, which is a significant space weather platform. GOES already is as well, and Discover. But we're leveraging heavily many research assets. And we do that now out of necessity because we don't have research assets, operational assets for space weather. But this is an area even more so where I think a disaggregation or a distribution of small satellites is going to provide probably the way that we do better situational awareness, in situ measurements of the Earth, near Earth atmosphere environment for space weather. And this is a place where NOAA is working with NASA and with other, with NSF and with other agencies to try and figure out the best way to take research assets and use them operationally. And we are already within the Space Weather Prediction Center. So I want to give you one case study, which is how you go from research to operations. That's what R2O says. Because the question is raised is how does a research instrument that you guys are doing ever turn into an operational asset, or is there a graduation plan? Is there an evolution plan? The geostationary lightning mapper that launched last week or 2 weeks ago was the first time it's ever been in geostationary orbit. But it didn't start yesterday. It started in the in the 80s. In 1987, Steve Goodman, a researcher, flew the first one of these on a U-2. And we'll talk in a minute, it flew in others. By the way, Steve is now the program scientist for GOES-R. It took him 30 years to get it from a U-2 satellite airplane flight to a geostationary. I wouldn't recommend that as your path for a resolution, but in the process, every step of the way, he added extra information to it. So he flew it on a G2, U-2. It flew as a microlab, as a demonstration again. A similar measurement flew from LEO, and it was demonstrated as a small payload. It's on the order of this big, I believe, sitting on the TRIM, the Tropical Rainforest Measurement Mission, and provided data for almost 20 years. And there's another version of this going to be flying on the ISS coming next spring. It's the engineering model of the one that was built in 1997. So you can imagine this hardware is extremely old. But the technology, it's not just the technology, it's the utilization of it and the integration of it into the system that is really key. So these prove that the observation is useful. And then advances in detector technology and in signal processing to be able to filter out lightning against a bright background on a daylight sky, for example. Allowed from filtering and the spatial resolution definition and how to pick the right spectral band for pinpointing lightning against just reflected sunlight or over clouds or over water or over ice was all kind of key in determining what exactly would go into GLM. And that's what led to the GLM we're going to see now and will provide one other thing, what Stephen Goodman was able to do over the years was to show how this measurement could be critical in understanding storms and understanding the start of tornado events and how it feeds back into the cloud interfaces and the dynamics of a storm processes. Without that, there's no rationale for doing it. It's cool watching lightning, but why? What's the value of it? Because it makes us smarter in understanding storms and in storm intensification in a way that we can't get any other way, which is the real rationale for doing it. So, as a transition then to the last, so it's really about operations and research. I talked earlier about NASA and NOAA are really essential partners in this, but it's research and operations are the partners here. We couldn't live without each other. The capabilities of what we fly now are really climate-grade instruments which have operational use. And when you look at that picture that we just had a minute ago of GOES-R, and I'll get to that in a minute, well, I'll get to that, but it's showing capabilities that are beyond what we promised or what we committed to in order to build these. For example, when you look at things we're doing now with JPSS, with VIIRS instrument, it has a band on there which is a day-night band, they call it. It's very sensitive. We can do weather at night. We can measure clouds and ice. We can monitor that from in the Arctic at night without sunlight in a way we've never had before. So there never was nighttime cloud monitoring. But the day-night band on VIIRS is sensitive enough so you can pick out clouds and see storm fronts at night. So that is that's our nighttime geostationary orbiter because VIIRS crosses over the North Pole 14 times a day. Near real-time continuing monitoring of ocean color and current in a way that we've never had before. The geostationary can now, with a resolution, see ocean currents at a resolution and scale that never been happened in the past. Usually a pass every day. So you collect it over a couple of days and you get some information. With real time now, we can monitor and watch current flows in a way never before. And the climatology, the accuracy and the resolution are such that we now have a data record 30 years past and indefinitely into the future, which allow comparison on first principles of what you see today and what we saw in 1990. and what we might see in 2050. So every time we apply a new platform, we meet the requirements, but we also open up a bunch of different possibilities that we are not funded to support, but is there for exploitation from the research side. And just two quick examples. Here's the VIIRS nighttime light detection monitoring. They realized using this technique, they can use it for storm impact assessment. Power outages are much more easy to determine and quickly using VIIRS with the first pass right after a storm than it is to go out and call people up and say, is your power up or down? So it allows resource managers and emergency managers to say, I've got a black area here, which is bigger impact using this comparison with one without the power outage. This is where I need to send my people before I get a phone call from them, because the lines might be down all throughout that area. Similarly, you can see that we've seen flood mapping, which do the same thing in a way that hadn't been predicted. Another example, using that same day-night band, we can detect ships at night. We don't have the resolution to see the ship because it's like 200 meters, but we have the sensitivity to detect the ship's lights. So ships illegally fish at night. This is the Sea of China, South China Sea. And with VIIRS now, you can see those ships. And you can see then, and if you were to draw a line, you'd see, here's the international fishing line. These guys are on the wrong side of it. These guys are on the right side. So this kind of tool is being used now in the North Atlantic, in the North Sea, and in the South China Sea, where you see a lot more illegal shipping than you ever would have, than was ever reported, because nobody has the time and the effort to send those boats out there to keep track of these. This is another technique. Eventually, this may go away because somebody else wants to fly a small sat that can do this and then can sell it. Okay, that's fine, but we've demonstrated the capability in something that wasn't in our proposal, so to speak, for VIIRS. And I put this back up just as another example. If this is my next to last slide. If you're a researcher out there, what do you think you can do with this kind of information in 16 spectral bands with a resolution and a time frame that you can do atmospheric dynamics in a way that you never could do before? A low Earth orbiter has high resolution, but it passes once a day. This is going to measure the entire diurnal cycle. And you can look and see a storm start at dawn and then propagate over the next 6 or 8 hours. And you can look at it in infrared and invisible wavelengths. And you can look at it and see how other effects change it in a way. I don't need that. I only need this to do the imagery for the storm forecasters. But the research side, the NASA researchers in particular, how they can map this against hyperspectral measurements from LEO to get the combined integrated products is going to be incredible. And it's going to, as we've said, it's going to take us a generation to figure out how to use these data. And that's how long we're going to be flying them before we come up with the next system. So this is sort of my last chart, which talks about how we bring all these together. The global observing system is, we have the satellites, but we also have the ground systems which have to monitor these and integrate those. But the part I didn't get to, which is really, I think, equally important and challenging, is how we integrate all these data sets together, how we understand the processes that are taking place, what our computers are able to handle, what our models are able to do to take the numerical models and to integrate these into an ecosystem modeling. And that's the part the Weather Service is a provider on that, but also the Department of Energy. There are lots of players in that. We had a conversation, I was talking to Mike earlier about the space physics side of that. What is the space dynamic side, determining this from the surface of the sun to the surface of the Earth? All those models and the integration of all those is the real challenge we have going forward. But the challenges are there, but we're in the process right now of doing this architecting, of preparing for that future within the NESIS and within NOAA. So my last slide here, let's see, I'll go past those, is we never forget who we're working for within NESIS and NOAA. It's not about just doing research. It's about providing, driven by user needs. It's committed to providing thorough validation, so we are the trusted source. Nobody has to question whether the data are accurate. Doing it 24/7, 365 forever, so there's no interruption services. And also making sure that we're open to all sources of data. We have to be ready to use whatever is usable to make it, to meet our services and our needs. So with that, I'll leave time for questions, I think, and I thank you for your time and attention.
Have such a violent launch on top of millions of pounds of thrust. Ridiculous vibrations. So we actually have a vibration table in the Space Physics Research Laboratory that allows us to shake the satellite at very high rates.